How are you?
I'm good. How are you?
I'm okay. Let me uh let me get this in focus. And you can tell me how it looks. Welcome to office hours. How does that look? Is that in focus?
Yes.
Great. What can I do for you?
I had a question about special homework 10.
Mm-hmm.
I know you did an office hour, I believe last week or recently about it. No, this week. Yeah, this week is
We
just
did one Sunday and we did one Monday.
yeah.
But we didn't talk about special homework 10. We talked about special homework 9 on Sunday and Monday.
Okay. Yeah, my question is about
Or was it 10?
I think it was one of them was 10.
Oh, it was 10. That's right. That's right. It was 10. We did talk about it. Uh-huh.
Yeah. Um, I was question one out of all of them is the one that's giving me the most trouble. I don't know why.
Read question one to me.
It says, let A be a set and suppose that A1, A2, three dots, AN is a collection of subsets of A. Write the three properties that this collection must satisfy in order to be a partition of set A.
So, did you see the hint? What does the hint say?
See class notes and watch your indexing.
So, did you see the class notes?
Yes.
Okay, I'm going to share my screen with you.
Okay.
Right. So, let's take a look at class notes. And this is definition of a partition.
Mm-hmm.
So, I think it's going to be from day 19. Let's see. I don't know why this isn't showing up. Do the other pages of the note show up for you?
Yes.
I don't know why it's not showing up. So can you see page, this is day 19. It's so weird. I wonder if it's just taking it a long time to load. Can you see page 7
Yes.
of the notes from day 19?
Mm-hmm.
Is the definite, I don't know why it's not showing up here. Uh, is the definition of partition on page 7?
Yes, I see the definition.
That's it. It's a three-part definition. You just need to copy that.
Oh my gosh.
Everything you need, you're going to find it in the notes. I don't understand why this isn't showing up on my computer. You know what? My computer RAM is probably smoking. Between Zoom and having stuff open, it's probably just rammed out. Okay. So, next question, Abu. It's your turn for a question. Good to see you.
Oh, very funny. I saw it.
Shall we
So
look at
what
some
I,
intersections?
yeah, please.
Okay, so intersections involving interval notation. And this will help you too, Malayla. Okay, so let me just make up some examples. Can you see this okay? All right, so let's just make up an example. Let's let A be the set that goes from uh, -2 to 3 and a soft bracket at the 3, square bracket at -2, and B, let's say it goes from -5 to 0, square bracket both places. Okay? Now, this is interval notation. These are real intervals. So both of these sets are infinite. They've got infinitely many elements. And now we're going to find, well, we can do several. We can find A intersect B, and then we can also find A union B. And if you want, we could go ahead and find like A minus B. Would that help?
Yeah, sure. Yeah.
All right, so we'll do intersection first. But honestly, what's going to help us the most is to draw a picture. So let's draw a picture, okay? All right, so A, we're going to do set A right here. Okay, this is the real line. All right, it starts at -2. This one's got to go back to -5 though. So I'm going to say -5, -4, -3, -2, -1, 0, 1, 2, 3. Okay, and then we'll draw B and we'll line them up. Okay, -5. Well, actually, I can just put them like that. Okay. That way I don't have to rewrite the numbers. All right, now A starts at -2. So here at -2, and it includes the endpoint because it's square, we'll put a square bracket here, okay, at -2. So we're starting at -2 and we're including -2. Can you see it okay? Get a little closer. Now, A goes to 3, but it does not include the 3 because this is a soft parentheses. So it's everything starting at -2 and include the -2. We're going to sneak up on 3 from the left, but we're not going to include the 3. You with me?
Mhm.
Okay. Now, B starts way back at -5. So here's our -5, okay? And it includes a -5. And it goes to 0, right? And it includes the 0. And it's everything in between. It's not just -5, -4, -3, -2, -1, 0. No, no, no. There are infinitely many points in here, tons and tons and tons, more than we can count. You with me?
Yeah.
Now, the intersection is going to be the region that overlaps. Remember, A intersect B, it's going to be the X, here the domain in the reals, such that X is an element of A and X is an element of B. Does that make sense? So, look, is a -5 going to be an A intersect B? No, because it's not in the A.
Yeah.
What about -4? Is it going to be in A intersect B? It's in B, but is it in A? No, because A doesn't start until -2, see? Then we go to -3. -3 is an element of B. Do you understand that -3 is an element of B?
But because between the five.
Yeah, but it's not in A, so it's not in the intersection. But now we're at -2. -2 is an element of B because it's sitting here in the middle of all this dark area that's all the elements. Is -2 an element of A? It is. So this starts at -2 and includes the -2 because it's -2 is in both of them. Are you with me?
Yeah.
Now, so from -2 all the way to how far do we go? This is the overlapping area. Stops at 0 because that's where B stops. Is 0 in A intersect B?
And B.
It's in B. And
Yeah. Yeah.
look, it's right, yeah, it's right here, smack dab, inside of A. So it's in both. So we put a squared bracket on the 0 because it is in both. All right. Now, A union B is defined to be the X in the reals such that X is an element of A or X is an element of B or both. You know, we always use the inclusive or. So,
That's all five to negative five.
yes. So tell me what kind of delimiter, square bracket or soft bracket at the -5?
Include the five.
Square bracket.
Square
Include the -5. Good.
bracket.
And then how far do we go?
Right before we get to three.
So soft bracket. Now let's look at A minus B. We start with the elements of A. So anything in A minus B has to be in A to begin with. So anything from -2, including -2 to 3, those are the only candidates to be in A minus B. But now we have to subtract away the elements from B. So we have to take away all these elements in the overlap, right? We got to take them away because they're also in B, you see? So something's going on at 0. We have to think carefully about whether or not 0 should be in A minus B or not, right? Because we need to know whether to start it with a soft bracket or square bracket. We know it's going to start at 0, but the thing is, do we include the 0 in A minus B, or did we subtract the 0 away because the 0 was in the B? Is 0 an element of B?
It's there.
Look, see the square bracket here?
Mhm. It is.
It's it is. 0 is an element of B.
Mhm.
So we have to subtract it away from A. So what should we put here?
Soft bracket.
See it? And then, so the elements in A, we've subtracted all this stuff. So how far do we go? 3, soft bracket, because that's where A ends. Does that make sense?
Yes, got it.
Okay. Malayla, it's your turn for a question. What would you like to ask now?
Could you explain C again? I didn't understand that.
Okay, so set minus is this. A minus B is the X's in the reals. Now that's just because we're playing real number line games. It might be another domain. If it's a finite set, it might not be this. But we're playing in the domain of the reals. That's our default domain, such that X is an element of A and or but X is not an element of B. We have to throw away from A any elements it shared with B. And those are the elements between -2 and 0. We had to throw those away because those elements are part of B. And so we're left with the elements from A that are here in the clear. Does that make sense?
Mm-hmm.
And we
Yeah.
have to think carefully about, where A minus B starts because we know that after 0, we're in the clear. The real question is, do we have to subtract 0 away from A? Or should A minus B have the 0 in it? In other words, do we need a square bracket here or soft parentheses? Well, we're looking at taking away all the elements of B. 0 is an element of B. You see, because we put a square bracket there, that means 0 is in B. So we have to subtract the 0 away from A, just like we had to subtract all these other numbers between -2 and 0 away from A because they are in B, so we can't have them because we have to throw them away. So we start just to the right of 0. And then we go all the way to the end of A. These are the elements that are in A, but not in B. You see?
Mm-hmm.
Does that help?
Yes.
You're welcome. Next question. Really, pictures help. We can play this game, it's a lot easier to play these games with finite sets, right? It's just tough with interval notation, but let's do a set minus. Let's say that the universe is the set with little a, little b, little c, little d, little e, little f, and little g in it. And let's say A is the set that has A, C, D, E, and B is the set that has E, F, and G in it. Okay. And let's find each of these sets. It'll be a lot easier with a finite set. Let's find A union B, A intersect B, A minus B, and A complement, because the universe is given, we can find the complement, which is everything that's outside of A, okay? So let's do this together. Remember, the union is our OR operator. It kind of looks like the OR operator. So the elements in A union B will be elements from the universe that are in A or in B. So tell me, what should we put inside our set brackets? Don't forget your set brackets to put into A union B, Malayla. Anything in A or in B.
Um, you said all the elements in the universe that are in either A or B.
Uh-huh. So let's go ahead and write those elements.
I mean, all both of them are in the universe.
These are subsets of the universe. When we're building this set, we want to pick those elements from the universe that and put them in this set, the union, if they are in A or if they are in B. So, for example, little a is in the universe, but it's also in set A.
Mm-hmm.
So, little a is going to go
Oh,
into the union.
okay. Then it would be C, D, E, F, and G.
Good. Now, the intersection will be elements of the universe that are in both A and in B. Don't forget your set brackets.
A,
A is in set A, but it's
it would be
not in
E.
set
Would only
B,
be E.
just E, yeah. Now we'll practice set minus, set difference. Start with A and subtract away any elements from A that are also in B.
It would be A, C, D, F, G.
Ah, wait a second.
Oh,
Are F and G in A?
no.
They're in B. We don't want them.
Oh,
Elements of A minus B have to be in A to begin with. And we
okay.
just subtract away anything that overlaps with B.
Then that's it.
That is. And to find a complement, by definition, a complement is the X in the universe such that X is not in A. So we're looking for elements from the universe that are not in set A. It's exactly kind of the opposite of A. It's sort of like our not operator.
It would be B, F,
Yep.
and G.
B,
F.
B, see, C is in A, D is in E. Oh, what about F? Did
Yeah,
you?
I said B, F, and G.
Oh, I'm so sorry. I did not hear the F. Yep, you're right. Does that help?
Yes.
Okay, your turn,
Mhm.
Abu.
So, so Professor, for the A or B, can't say really close, but so I was just I thought that A or B is the same thing as everything in the universe.
No,
It's not.
no. A union B,
Uh-huh.
these elements have to appear in A or in B. So for example, this element little b, it does not appear in A or B, so it's not going to be in the union.
Makes perfect sense.
See, because little b is not in A and little b is not in B either. So it's only A, C, D, E, F, G that are in A union B. So in fact, the fact of the matter is A union B complement, the only thing that's not in A union B is this element right there. Now, a nice thing to do is to look at these same sets and do later. Okay, I'm going to give you some do laters. And there was a really nice collection of do laters in the class notes as well. And you should do those if you need the practice. Let's find A complement intersect B complement. So the first thing you have to do is find A complement, then find B complement. Once you've found those, you want to find the intersection, right? Then the next thing to do is to find A intersect B complement. Well, we found A intersect B. So the complement of A intersect B is everything in the universe but the E, right? So it's like A, B, C, D, F, G. See what I mean? So you'll be able to find that and then find A complement union B complement. And then test. Was your A union B complement equal to A complement intersect B complement? And also, was when you find A intersect B quantity complement, does that turn out to equal A complement union B complement? The answer to both of these should be yes, because De Morgan's laws for sets are just here and here. These are the De Morgan's laws for sets, okay? And you can compare them to De Morgan's laws that we learned for the and the or and the not. You should compare these to those De Morgan's laws, and they look a lot alike. Union is the or operator, intersection is the and set complement is like our not operator. Okay, Malayla, it's your turn for a question. Do you have a question?
No, I I don't have a question.
You do not have a question?
No, I'm okay. Thank you.
Abu, do you have another question? Have you had a chance to look at the quiz questions yet, Abu?
Yeah, I started doing it. As a matter of fact, it's should have some, yeah. But
I'm going to share my screen and we'll look at it.
okay, please.
Professor,
Yes.
I can't find it on Blackboard.
Okay, well, let me take a look.
Sort of the 21, I
See
think.
the class notes, day 21? There it is right there.
Oh, I thought it was with
Well, it
with
should be
the
also in the quizzes folder.
yes, I had taken a look at it, but I thought it was under the special homework.
It's also I sent an announcement telling you where to find it.
Yes, I saw it.
Well, then I said it was with the notes or in the quizzes folder. Anyway, here it is. You know what? We proved the other subset inclusion in class. You see, the thing that we learned in class was how to prove, well, you were there last time when we started proving subset inclusion, right, Malayla?
Yes.
So we were just continuing with more proofs for subset inclusion. In fact, this could be an equality. This subset inclusion goes both ways. I believe in class we proved the direction in the other direction that A union C minus B is a subset of A minus B union C minus B. Oh, this is a take-home quiz, right? All right, so we're asked to prove that A minus B quantity union C minus B is a subset of A union C quantity minus B. Okay, I'm just going to write that down. And hang on, I want to navigate again to the class notes because in the class notes, we proved the other direction of that. Let's take a look. See how we proved the other direction?
Mm-hmm.
So you can actually use this example one from class to help you because you're going to be basically going backwards. You know, you're going to start with an X that's in C minus B union A minus B. It's going to be in either C minus B or an A minus B because we break down the union first. So let's just go through kind of the process. For the proof, of course, you can always say let A, B, and C be sets. And is there nothing wrong with skipping that because we know these are sets, but if you want to just write that just to get yourself writing, that's good. All right, now we've started writing. Now we have to remember the strategy. If we're going to prove that this set on the left is a subset of the set on the right, we have to remember the definition. Subset inclusion means if X is an element of this set, A minus B union C minus B, then it must be that X lands in the other set on the right, A union C quantity minus B. So this is what we have to prove. We have to start with an X over here in this set, and we chase it until it lands in this set. Does that help get us started? So what would we assume? What would our first assumption be for this proof?
X belongs to A minus B union C minus B.
That's right. We start with an X in A minus B union C minus B. And what do we wish to show?
A union C minus B.
That's a partial answer. But this, if all you say is we wish to show A union
Oh,
C
no,
minus,
X is an element.
Good.
A union C minus B.
Exactly. We need a complete thought, don't we? Very good. And then the other main thing to realize is when we are trying to break down what it means for an element to be in some complex compound set, we break down the set definition starting with the last operator that would act. So we break down starting with the last operator. This union happens after these set differences happen, right? So we start by breaking down this union, and that always gives us cases. Because X is in this union, we know X is in A minus B or X is in C minus B because union means or. And that means we have two cases. Whenever we have or, we have to set up cases. Case one would be that X is an element of A minus B. In that case, we want to show that X winds up being an A union C minus B. Well, X is in A and X is not in B if it's in A minus B. Since X is in A, X is in A union anything, including A union C. So if X is in A, which it is, X will be in A union C by definition of union. We also know X is not in B when X is in A minus B because definition of set difference was X is in A and X is not in B. So X is still not in B. So X is now in A union C and X is still not in B. So X will be in A union C minus B by definition of set difference. And then you can do the same thing for case two, because we don't know which set X is in. All we know is X is in A minus B or it's in C minus B. We don't know which, but in both cases, we'll be able to chase X into this set A union C minus B. Because if it's in A minus B, it'll be in A, so it's in A union C. If it's in C minus B, X is in C, so it'll be still in C union A, which is A union C. And it's still not in B in either case. So I think that you'll find that the class notes can help you as you try to write that proof. And exercise two looks almost exactly like the proof that we did in class, the very last proof on day 21. So see day 21 class notes, last example.
Contradiction.
It'll help you so much. And this example is also in WebAssign. Like you should check out WebAssign, if you just want to poke around, maybe not answer the questions, but take a look at them. I think some of those questions might be these. Like there's quite a bit of overlap. Next question.
Oh, but man, I do have a question, but I wanted to see.
Um, that was all the questions I had. Thank you, Professor.
Malayla, thank you so much. And how is your arm feeling, dear?
I'm feeling good. I'm feeling good. I have 2 more weeks of this, so
Oh my
looking
gosh,
forward to taking it off. But thank
I'm
you so much
sure.
for asking. I'm doing great. Feeling better.
Okay,
Just trying to rest whenever I can and take breaks when needed. So, yeah.
good. Very good. I'm glad to hear it. We'll see you
Hmm.
tomorrow.
All right. I'll
Oh,
see you tomorrow. Thank you, Professor.
good night.
Good night.
So, Abu, what would you like to look at? Anything. We can look more at intersections or whatever you want.
Okay, so yeah, for whatever reason, I thought tomorrow was that test at 3.
Oh, you thought tomorrow was the test, you poor thing.
Didn't leave.
Oh, well, take a breather. Take a breath.
Yeah,
It's not until Tuesday. You have all weekend to study, and I'm going to post a list of practice problems for you tomorrow.
it's so awesome. Okay, so Professor, I was looking at the same 6.1 part 2 date one.
Uh-huh.
And then you had a problem here, which was on proving subset inclusion, um, and it was for two integers. Uh, yeah,
All right. Tell me
well,
which.
you know,
This was the one we were talking about today, wasn't it?
yeah, the one for yeah. So I normally just go over the.
All right. So here's the definition up top. A sub I equals minus 1 over I, comma 1 over I, and we're including the endpoints. Do you agree?
Yes.
So when I equals 1, I mean, you understand how to get these intervals, right? By plugging in I equals 1, 2, 3, 4. So that's not the problem, right?
No, no, no. And the
Do,
only problem I had with this one was understanding the intersections, which you explained earlier. Because I couldn't understand how to get the intersections.
well, do you see though that, I mean, look, my numbers aren't lined up perfectly, okay, but you see what I mean? Like my number line's not perfect. The 1/4 maybe is a little, I don't know, a little too far over that way. But the point is, everything that's in A2, all these between negative 1/2 and 1/2, they are all in A1, right? Plus A1's got stuff out here and out here that isn't in A2. Like between negative 1 and 1/2, those elements are not in A2. See how it's blank here at A2? So these cannot be in the intersection because they're only in A1. They're not even in A2. They're certainly not in A3 or A4. So we have to cut out everything from negative 1 to 1/2 right away. Same way with everything from 1/2 to 1. All these elements out here on the right in A1, they're not in A2. So they certainly aren't in A1 and A2 and A3 and A4. They're only in A1. They aren't elements of A2 or 3 or A4. See? So we have to cut those away. Because in the intersection, we can only take the elements, the real numbers that are in all four of these sets. And every time we step to the next A sub I, so like from A sub 2 to A sub 3, we have to cut some stuff out. Because like negative 1/2 is an element of A2, but it's not an element of A3 because it's outside of A3, see? And 1/2 is outside of A3. So this little amount here and here that is in A2 is not in A3. Does not having the dealy bops, is it, should I be drawing the dealy bops where the 1/2 is here and the negative 1/2 is here? Do you need to see those?
But that's the, you could see it.
Okay. And the bottom line is because A2 is contained in A1, the intersection of just plain old A2 and A1 is A2. Everything in A2 is also in A1. But we're not just intersecting A1 with A2, we're also intersecting it with A3 and A4. In other words, anything that is in this intersection has to be in all four of these. Well, that's going to be the littlest set because these are nested. So only these elements between negative 1/4 and 1/4 are actually inside all of these other sets above. You see? That's why the intersection is minus 1/4 to 1/4. And it's special because these are nested.
So, Professor, so while you was at it, if we go down, what was it? D. So, so D, it looks like, so it began at one and
Yep,
it went all the way up to N.
yep.
So, so why was the So why is that equal to, so is that equal to everything in the given set?
Yeah, because look, do you see that A5 would even be smaller than A4?
Right, yeah, yeah.
And A6 would be even smaller than A5?
Uh-huh.
And A100 would be tiny, tiny. But when you're taking the union is the or operator. We already have everything from the get-go. A1 contains everything the other sets contain plus more. It's the biggest set, and the other sets are all subsets of it. So it doesn't matter how many of these you union together, these just get tinier and tinier and tinier. They don't contribute anything that wasn't already there at the beginning with A1, because A1 was the widest one. Like unioning with more and more doesn't help you. It doesn't build anything more. Everything you're going to get, you get from A1. Union means or. So an element is in this union if the element is in A1 or in A2 or in A 100 million. But listen, everything that's in A2 is already in A1. So anything in A1 or A2 is going to be in A1.
So the N is just like saying any number you, so
Yeah.
oh,
It could even be one. It just could be just A1. Or it could be A1, union A2, union A3, union up to A 1 million. It's still already there with A1.
because this given universe, you would say it's from -1 to 1, right?
Yeah. Yeah, in some sense, that is the universe because all these other sets are subsets of A1. That's a good way to think about it. It's the biggest set around, you know. But when we intersect forever, now that's different. See, when we intersected to four, A1 intersect A2, intersect A3, intersect A4, we were limited to just everything between -4, 1/4, and and +1/4. Sorry. See what I mean? Because these were the elements that were in A4 and in A3, they're in A2, and they're in A1. But if we keep intersecting out forever, then these sets just tighten around zero, closer and closer and closer. And the only element that's guaranteed to be in all of them is the zero. That's the only thing that you are going to be for sure is in A sub whatever forever. See, because 1 over n gets really tiny. As n gets big, like 1 over 100, that's small. 1 over 1,000, ooh, that's tinier. 1 over a million, teeny, teeny, tiny. 1 over a gazillion, so tiny. But 0 is still going to be sitting there. So it's the only thing we're guaranteed will be in all of them when we just keep imagining intersecting forever and ever. The 0 won't ever go away. It'll still be in between the square brackets, no matter how close the square brackets get.
Uh, Understood.
Good.
Yeah. And then you had 6.2, it's down further down. No, the other way. Yeah. All the way.
Yes, this is when we first started talking about sort of the basic principles of
Mm,
proving subset inclusion and set equality. So
yeah.
I think on this day we didn't actually get to set equality. but we did define what it means for X to be a subset of Y. And that happens, X is an element of X implies X is an element of Y. If that implication holds, then X is a subset of Y. So that's why we take an element from big set X and we chase it into set Y. We're showing that if we have an element little x in set X, then that element can be chased into set Y. And that's the definition of subset. It's an if-then definition. If the element is in set X, then that same element is in set Y. And we have these little facts. The empty set is always a subset of Y, no matter what Y is. And Y, of course, is a subset of itself. Did you understand why the empty set is a subset of Y for any set Y?
Nothing.
Because it's an if-then definition. If X is an element of the empty set, right? The empty set is our big set X. Then the element little x is an element of Y. Well, X is an element of the empty set is always false because
Yeah.
empty set's got no X in it, right? And do you remember that if we have an if-then that has a false hypothesis, then the whole if-then is true. And that's why the empty set is a subset of every set because it's false hypothesis. There is no element little x in the empty set. And so here's our strategy. It's the element chasing argument. If you want to prove X is a subset of Y, assume element little x is in this set we want to prove is a subset, and then show that X is in set Y.
And then this is the one I had
This is a fun one because it's so against our intuition.
so yeah, so that's was went over it, but I couldn't.
Okay, so
Have
let's go through it. Here's our strategy right here. If we're
Mhm.
going to prove A is a subset of B, right? We're going to assume that X is in A, and then we're going to chase X and show it's in B. Does that make sense?
Mhm. Mhm.
So we assume X is in A, right? We wish to show X is in B. So you understand the strategy of subset inclusion proof?
Yeah.
Great. Well, then we just use the definition. By definition of set A, X looks like 12K for some integer K, right? I mean, that's just how A is defined. A is the multiples of 12. 0, 12, 24, negative 12, negative 24, 36, negative 36, 48, negative 48. These are the multiples of 12, okay? They have 12 as a divisor.
12 times a number.
Well, the thing is, the 12's got the 4 in it. See, we can pull a 4 out of the 12. See, if X equals 12K, can't we just rewrite that as 4 times 3K?
Mm.
And 3K is an integer because K is an integer.
Uh,
So if X looks like 12K, it also looks like 4J for some other J, for J equals 3K, see? And that's what it means for X to be in B. It's a multiple of 4. Multiples of 12 are multiples of 4. They are also multiples of 3. A multiple of 12 is a multiple of 6. A multiple of 12 is a multiple of 2. But we think it should be the other way around, right? We think it should be that B is a subset of A, right? Because we're looking at this 4, and 4 is smaller than 12, right? So we think B is going to be smaller than A because 4 is smaller than 12. But the algebra doesn't work that way. Here, let me show you. Let's draw. Okay. 0, 4, 8, 12. 16, 20, 24, 28, 32, 36, okay? 0 is a multiple of 12 and a multiple of 4. I'll make these a little bigger. 0, 12. Okay, and let's go back. -4, -8, -12, -16, -20, -24. All right. Now, A is the set of X and Z such that X equals 12K, where K is an integer, right? All right, so we're going to use a black box around the elements of A, okay? 0, 12, 24, 36. We can go back to -12. All right, do you agree that those are the multiples of 12 on that number line? All right, now B is a set of X and Z such that X equals 4J, where J is an integer. We'll put a circle around the elements of B, okay? 0, 4, 8, 12, 16, 20, 24, 28, 32, 36. See what I mean? Look how many more of them are in B. Because that multiplier is smaller, there are going to be more integers in B than in A. The integers in A only come every 12 steps, jumps of size 12. But the elements of B come every jump of size 4. There's a bunch more of the integers in set B. B's got 3 times as many integers in it as A. See, I mean, we think that B should be a subset of A, right? Because 4 is smaller than 12, but it's the other way around because the elements of B come quicker on the line. There's more of them. They're more densely packed in here, whereas the A elements are spread further apart. There's not as many of them. Isn't that cool?
Yeah. Yeah.
Do you want me to give you a do later?
Sure.
I see that you're in the room, Jessica. I'm glad you're here. All right.
Hi, Professor. How are you?
Working, working.
Yep.
All right. So let's try this. Let's let C equal the set of X in the integers such that X equals 5K for some integer K. All right. And we're going to let D equal the set of X in the integers such that X equals 10K J for some integer J. Part A, find 8 elements of C, do the same for D. Now, I don't care whether you just list the elements or if you make a number line, but I want you to look at the elements. Which is true? C is a subset of D, or D is a subset of C. Which of those is true? Prove the true statement. And that will force you to go back and look at those class notes one more time to get guidance on how to prove the correct statement. And drawing a picture like this will give you insight into which of these two sets is really the bigger set. Okay? All right, folks, I have been at it since 6:30 this morning. I had meetings all day and oh my goodness, I am going to have to call it a night. Thank you so much for coming in. I hope you learned something.
Thank you very much, Professor.
Thank
You're
you,
welcome.
Professor. And
Good
then I'll
to
just
see
email you
you.
if I have any additional questions.
Yeah, I'm just out of energy now.
Yeah,
Good
no,
night.
I'm sure.
Yeah, good night.
Good night. Thank you.